A German mathematician named Georg Cantor published 1874 his proof showing that there is more than one kind of infinity. Only 2 years later, after Raymond's keynote, which we discussed in my last video, in which the physician Raymond argued that there are some fundamental limits scientists and the human intellect could never cross. Raymond ended his keynote with his famous quote, "Ignoramus et ignorabimus," which translates into, "We do not know and we will never know." Cantor's main contributions to mathematics dealt with what we call today set theory. What Cantor has achieved in his proof 1874 seemed to contradict Raymond's pessimism. But as we will see in today's video, Cantor's way of dealing with infinity in mathematics opened yet other floodgates, putting the foundations of mathematics even more at risk and finally causing a major crisis in mathematics. For Cantor, a set was simply a collection of some well-distinguishable things. Nowadays, that would not be a valid mathematical definition, and the way Cantor defined sets is probably the root cause of the upcoming foundational crisis in mathematics. Still, at the time of Cantor, it seemed to be sufficiently precise. In today's video, I want to show you why many contemporary mathematicians thought Cantor was opening Pandora's box in mathematics with his set theory and hazardous way of dealing with infinity. One of Cantor's important observations was to propose a method of comparing the size of two sets without actually having to count the elements of these collections. He observed that if we have two collections of things, like we see on my slide, some items labeled A, B, C, D, and etc., and some boxes, then we can establish a one-to-one correspondence between their corresponding elements. If we are able to do that, then both collections have to be equal in size. They will have the same number of elements, no matter how many elements they have. But occasionally, we will fail to find such a one-to-one correspondence and only find a one-to-many correspondence. Then, the collection on the one side of the correspondence will be smaller in terms of the number of its elements as compared to the collection on the many side of this correspondence. On my slide, for instance, one box was left empty. Finally, there will be occasions when we only find a many-to-one correspondence between the two collections. In this case, the second collection will have fewer elements than the first one. Note that we still do not have to count the items and the boxes to find out which collection is more numerous. Cantor's ingenious idea was to extend this simple observation to infinite sets. For instance, by finding a one-to-one correspondence between all infinitely many natural numbers and all infinitely many even numbers, Cantor proved that both sets have, in some sense, the same infinite number of elements. Well, this is a surprising result, because even numbers are a strict subset of all natural numbers. Intuitively, when you filter out some elements from a collection, you will get a smaller collection. But Cantor discovered that this holds only for finite sets. Things get much more different for infinite sets like the set of all natural numbers. This is only one of Cantor's weird discoveries, and if you have watched this video so far, I promise it will become even weirder and more fascinating. Note that Cantor's discovery is based on how he treats the infinity of natural numbers as an actual infinity. If you watched my video from Euclid's Elements to Leibniz's Characteristica Universalis, you will remember the difference between actual and potential infinity. Cantor always deals with actual infinities. He puts infinitely many elements into a thing he calls a set and deals with this collection as a whole like it was a new mathematical entity. And this approach leads him to many new fascinating discoveries. There were prominent mathematicians preceding Cantor, including Poincaré, Gauss, and Cantor's own teacher, Leopold Kronecker, who categorically rejected the idea of actual infinity in mathematics. But Cantor ignored this and took the existence of actual infinities for granted. That led him straight away to new discoveries when he tried out his method of comparing the size of two sets by comparing the size of a set to its power set. You may already know what a power set is. Given a collection of things that is our original set, we can occasionally or we can easily create its power set. It is the collection of all collections that we can create using the elements of the original set. For instance, if we have a collection of 3 things, we can start with creating the power set by putting in the only collection that contains no elements at all, then putting in the 3 collections containing exactly 1 element of the original collection, and then putting in the 3 possible collections containing exactly 2 elements of the original collection, and finally putting in it the only collection possible containing exactly 3 elements of the original collection. We will end up with a collection of 8 collections we can construct using 3 elements. 8 is 3 to the power of 3. And this result is no coincidence. It turns out that if we have a finite number, for example 3, of elements of the original collection, we will always end up with the number 2 to the power of 3, which equals 8 in our case, in the collection of its power set. More generally, if we have a set X and denote its size by putting X into bars, like we do for the modulus in mathematics, the power set will have 2 to the power of its amount of elements. And this is maybe the cause why it is called the power set, because it is 2 to the power of the element of the elements of the original set. This is the number of the elements of the power set in a finite case. But what does it mean for infinite sets? What would it mean if we had a collection of an infinite number of elements and then created a power set of it? Would we then get a collection of 2 to the power of infinity of elements? And what does it even mean? Cantor's ingenious idea was to answer these weird questions by proving that, given any original set, no matter if finite or infinite, and its power set, we will always only succeed in establishing a one-to-many relationship between the elements of the two. To Cantor's original idea, it means that the power set of any set is always larger in terms of the number of its elements than the original set. And this holds for both finite and infinite sets. For instance, we can only establish a one-to-many correspondence of the set of all natural numbers to its power set by assigning each natural number n to all the collections containing exactly n elements. So we could assign to the natural number 0 the only one set that contains no elements, which is the empty set. Then we would assign to 1 all sets containing a single natural number, and there are already infinitely many of them. Then we would assign to the number 2 all sets containing distinct pairs of natural numbers, and so forth and so forth. Note that this comparison does not rely on counting. It only relies on our ability to find such a correspondence and decide whether it is a one-to-many, one-to-one, or many-to-one correspondence. In the case of a set and its power set, it's always a one-to-many relationship. So, Cantor's second groundbreaking idea was to extend this idea to infinite collections. Now he could compare infinite sets according to the number of their elements. This was the first for the first time in history that he could do that. Note again that Cantor deals with sets as if actual infinity was possible. One of Cantor's next groundbreaking discoveries was that he managed to establish a one-to-one correspondence between the actual infinity of natural numbers, we often denote in mathematics with the capital letter N, and the actual infinity of all ratios or rational numbers we denote with the capital letter Q. In other words, there are countably many ratios because we can assign a single natural number to each of them. We can count them. So you probably wonder how we possibly can establish a one-to-one correspondence between all natural numbers and all ratios. Well, all we have to do is to find a systematic way of writing down ratios. To accomplish this, we start with writing down the rational number 0. Then we proceed with writing down all ratios with the denominator 1 or minus 1. The first two of them are 1 divided by 1 and minus 1 divided by 1. The next are 1 divided by 2 and then minus 1 divided by 2. Yet the next one are 1/3 and minus 1/3, and so forth. In the next line, we write down all ratios with the denominator 2 or minus 2. So starting by 2 divided by 1, minus 2 divided by 1, 2 divided by 2, minus 2 divided by 2, etc. In the third line, we write down all the ratios with the denominator 3 or minus 3. And we continue with all new lines. In each nth line, we write down all ratios with the denominator n or minus n. While doing so, we will come up with an infinite tabular schema. In each cell, we will have one ratio. Note that using this schema for a given rational number, we can always find a row and a column in which we can find it. Once we have found such a schema of writing down all possible ratios in a systematic way, we can now define a one-to-one correspondence between them and the whole numbers as follows. We assign to the whole number 0 the first ratio, which is also 0. Then we go one step to the right and assign to the whole number 1 the ratio we can find to the right in our schema, which is 1 by 1. Then we go to the right once again and find the ratio minus 1 divided by 1 there and assign the whole number 2 to it. Now we can change our direction and go diagonally down to the first column. This requires only one step, and we assign the whole number 3 to the ratio 2 divided by 1. Now we go down one step again, find the ratio 3 divided by 1, and assign to it the next whole number, which is 4. Now we start zigzagging, go up diagonally to the first row assigning 5 to the ratio minus 2 divided by 1, 6 to the ratio 1 divided by 2, 7 to the ratio minus 1 divided by 2. Then again diagonally down to the first column, we proceed with the whole numbers 8, 9, 10, assigning them to the ratios 2 divided by 2, minus 3 divided by 1, 4 divided by 1, respectively. And I hope you spot already the zigzagging pattern we are traversing the tabular schema. The zigzag pattern allows us to assign every single whole number to every possible ratio. Well, if you have paid a close attention to this approach, you might be objecting that our tabular schema does not contain every rational number uniquely. For instance, we will find the ratios 1 divided by 2, 2 divided by 4, somewhere to the right 3 divided by 6, 4 divided by 8, etc., etc. All these ratios denote the same rational number if we cancel out from their nominators and denominators the common divisors. So strictly speaking, not only our schema contains all rational numbers, but it contains each of it infinitely many times just in different notations. But note that this is not really a problem for our task of assigning a one-to-one correspondence between the natural numbers and the ratios. If you insist to have a schema with all unique ratios, we could remove from our previous tabular schema all duplicates and still be able to find a zigzagging way of assigning whole numbers to the remaining unique ratios. Now, as we know that there is a one-to-one correspondence between n and q, on the other hand, Cantor was able to establish a one-to-one correspondence between the power set of n and all real numbers, which we denote by the capital letter R. So look at it. This is a great discovery. Not only was Cantor able to prove that for every set, regardless of whether it is finite or infinite, the power set has more elements than the original set, but also that known collections of numbers like whole numbers, ratios, and real numbers have different sizes. For there is a one-to-one correspondence between q and n, a one-to-one correspondence between n and its power set of n, and a one-to-one correspondence between the power set of n and r. For me, these discoveries are totally counterintuitive, although they are still true. Cantor concluded that real numbers must be uncountably many. This is what we call today a continuum. Cantor denoted the first class of actual infinities with countably many elements with the Hebrew letter Aleph 0, and the first infinity with the uncountably many elements identified with real numbers he called Aleph 1. Cantor's groundbreaking ideas opened now the floodgates. Cantor started to play around with his actual infinities like with fire by creating their consecutive power sets, thus creating bigger and even bigger infinities, which we call cardinal numbers today. He proved that there is no such thing like the biggest cardinal number, because we always can apply a power set operation to a given set with a given cardinal number to get a set with an even larger cardinal number. But this led him to many new interesting questions that inspired many mathematicians for decades to come. For instance, he asked himself if there is some infinity in between the consecutive Aleph numbers. Cantor believed until his death that the answer to this question was no, but he never managed to prove his assertion. This later became known as the continuum hypothesis. As I said, Cantor and anybody after him could prove if the continuum hypothesis was correct until decades later. Paul Cohen proved in 1967 that this hypothesis could not be proved using the standard axioms of the set theory that were developed by Zermelo and Frenkel. By the way, and as we will see in a future video, these axioms were one of the approaches to heal the fundamental crisis caused by Cantor's set theory caused in decades to come. Another great question of Cantor that inspired many mathematicians after him had to do with the so-called well-ordering. A set can be well-ordered if, given any non-empty subset of the set, we can always find a minimum of this subset. For instance, the set of all natural numbers can be well-ordered because every non-empty subset contains a minimum. Surprisingly, it is possible to well-order all rational numbers. All we have to do is to find a way of writing them down in a systematic way, so we can count them one by one. As we already know, this systematic way of writing all existing ratios one by one establishes a one-to-one correspondence between natural numbers and rational numbers. Using this map, the well-ordering of natural numbers will induce a well-ordering over all rational numbers. Cantor knew this fact, and he asked himself if we could somehow induce a well-ordering on a continuum, which is a set with uncountably many elements. Can we well-order the real numbers like we can well-order the rational numbers? Like with the continuum hypothesis, Cantor was not able to answer this question during his lifetime. Ernst Zermelo, who also co-authored set theoretical axioms to heal foundational crisis of mathematics Cantor's set theory provoked, answered this question positively in 1904, and we will deal with his approach in a future video. I hope this video has shown you how Cantor dealt with actual infinities. His inaccurate definition of sets was a ticking time bomb, because many other mathematicians were very enthusiastic with his set theory and decided to use it to create a foundation of mathematics. We will deal with this subject in a future video. If you made it so far in this video, I really appreciate it. Please give it a like, leave a comment, and see you next time, guys, in a future video on the history of the axiomatic method in mathematics.